Good morning, everyone, and welcome back to Math 115. We got the laptop working finally. So today we are going to talk over sections 1.8 and 1.9. And as far as homework goes, I'm going to post a homework assignment today for 1.7. That'll be due on Sunday, I think. And then probably there will be a 1.8 homework, 1.9 homework coming sometime after that, which maybe it'll be due on like Monday or Tuesday or something like that. I don't need to talk about the next assessment because we just took the next assessment. So I'll tell you when the next one is next time. My office hours, I will be having office hours today from 2:30 to 4 in my office. Could I have a show of hands of who's planning on coming to office hours today? Okay, fewer people. So I'm going to hold my office hours in my actual office today. Okay? So I feel like that's a fine space as long as we have like 5 or less. If we have more, then we'll move to a classroom, but I'll send an email. Okay? So anytime that I'm doing my office hours in my office with just a couple people, I'm probably not going to record it, just FYI. It's just easier that way. So that's my office hours. If you can't make it to my office hours, go to the Math Tutoring Center. All right, that's all I have to say administrative-wise. Does anyone have a question in that vein before we start in on content for today? Okay, cool. Then let me start by reminding you what we talked about last time. If I can even remember what we talked about last time. Let's see. The notes will help us. Okay, we talked about function transformations, right? So we learned all of these different core functions, and then we learned a bunch of ways of how do we manipulate them all, right? So we learned vertical shifts, horizontal shifts, reflections, absolute value, stretching and compressing vertically, and stretching and compressing horizontally. So those were a lot of different ways that we could transform a function. And then we also learned that at the end of the day, when you have a lot of them all combined together, we had the rainbow slide to tell us that the order matters. Okay, so we need to do the operations or the transformations in this particular order. Okay. So that's something to memorize. We had an example then with everything, and then we started doing section 1.8, which section 1.8 is all about how do we combine functions. Okay, so the first couple ones that we learned were pretty simple. We can add two functions together by just adding the outputs. Okay, we can multiply two functions together by just multiplying the outputs, right? And of course, we can divide two functions by just dividing the outputs. But there was one additional thing that we had to worry about when we were dividing functions. What was that additional thing? Exactly. We have to make sure that that denominator is not 0, right? We need to make sure that denominator is not 0. Okay, so for the domain of each of these, okay, we agreed that as long as I can plug x into the sum, as long as I can plug x into each of the functions, right? So the domain of the sum of two functions is just going to be the intersection of the domains of f and g. Likewise for f times g, f minus g, and almost likewise for f divided by g. The only thing we had to worry about with f divided by g is we also need to remove from the domain any values of x which cause g of x to be 0. Okay, so we saw an example of that when we had f divided by g here, where f of x was given by this quadratic and g of x was given by x minus 2. So even though the domain of g of x, which is x minus 2, is all real numbers, the domain of f divided by g, we're going to throw out the possibility that x could be 2, right? Because we don't want to make that denominator 0. Even though we were canceling those two terms, right? At the end of the day, f divided by g was equal to this, but only if x is not equal to 2. Okay, only if x is not equal to 2. If x is equal to 2, then g of x is defined, it's 0. F of x is defined, it's also 0, but 0 divided by 0 is not something we can actually make meaningful sense of. So even though we canceled this stuff and got a new function, we need to remember where we came from, right? We need to remember that originally this was a rational expression, and this rational function, we have to be careful about the denominator. Okay, we can only simplify this in this kind of a way when the denominator is not 0. All right, so that was the domain of f and g. So I wrote it in some kind of crazy notation here. Let me just remind you what this means. So d of f was what I was writing for domain of f. D of g was what I was writing for domain of g. So I wrote r and r for both of those, okay? And then I did this symbol. This symbol means set minus, okay? So this is the way I take things out of a bucket. So I take a bucket. Into my bucket, I put all the real numbers. And then I'm going to reach into my bucket, and I'm going to take out the number x equals 2. Okay? I take out the number x equals 2. Okay, which you could also write as r set minus the set with just the number 2 in it, right? That means we take r, take out all of the numbers which are in this set, right? Or you can use interval notation. That's probably the most familiar to you all, so you can use that as well. All right. So that was what we did last time. Are there any questions on any of that content? Okay, doesn't seem like there are, so let's move on to talk about something new, okay, which is compositions of functions. And compositions are probably one of the things in the first chapter that give, or that in my experience, give 115 students the most trouble, okay, because it's a little bit abstract, and there's some weird notation, and it's a little bit confusing in terms of the order of things that are happening. So I just want to give that quick warning before we jump in. So a composition of functions is really about doing something like this, okay? We're going to take one function and we're going to plug it in as the input in another function, okay? As the input in another function, okay? And the notation that we sometimes use for that is this f, and then we do a little circle, okay? It's not a multiplication dot, it's a small circle. And that means composed with, okay? So this symbol here just means composed with. So the way you would read this is f composed with g of x, okay? Or something like that. Or if you want to write it like this, then you could read it saying f of g of x, okay? That's also fine. So those are that's the terminology that I'm going to use. So let's see how it works. Well, ultimately, what we're going to do is nothing different than what we have already been doing, okay? What we have already been doing is the following. If I have f of x equals x squared, and I want to know what is f of negative 2, what do? I plug in negative 2 for x, and I have to be careful, right? I have to plug with parentheses, right? I plug with parentheses. Okay, there's absolutely nothing different about what we are about to do, okay? So we plug with parentheses, and we get negative 2, we put it in parentheses, and we put that wherever there was an x, okay? And then we follow any rules that need to be applied, so we would get 4, right? No problem, easy peasy, right? We just plug in. Okay, f of g of x is going to be the exact same thing, except you know what we're going to plug in with parentheses instead of negative 2? We're going to plug in g of x, whatever that may be. Okay, so let's see an example here. So, okay. Well, maybe I should start with just a number. Okay, so let's start with just a number. So I know that I want to do f of g of 1, okay, where f of x is the function x cubed, and g of x is the function x plus 1. Okay, so I'm just going to use this right here to rewrite it a little bit first, okay? because this circle thing is kind of confusing. So I'm going to rewrite it as f of g of 1, right? So I'm putting 1 here instead of x, yes? So on the right-hand side, I put a 1 there instead of an x, okay? That's all I did. And now what do I do? Well, I use Pemdas. What does Pemdas say we should do first before anything else? The P stands for parentheses, right? Which means the first thing that I'm going to do is I'm not even going to worry about f, am I? I'm just going to do g of 1. Yes? Okay, so let's rewrite. I'm going to do f of, and then what I'm going to write inside of here is whatever g of 1 is. So the way I get g of 1 is by using this procedure that we just did, right? I'm going to take a 1 and I'm going to replace it right here. So what would I get? F of 1 plus 1, right? Which I can simplify to f of 2. And now to do f of 2, okay, I guess I should put a parentheses around my 1 to practice what I preach. So 1 plus 1 is 2. And then now what do we need to do? Plug in 2 for x in the f function. So now I cube it, and I get 8, okay? All right, so this is a new function, right? We start with an input, and after a while we get to an output, okay? It's a new function. If you want, you can view it, by the way. I'm going off script here, but I think this is useful. If you want, you can view it in kind of the following way. Remember how we said that functions are kind of like machines, right? And if we imagine that this is like a conveyor belt, yeah? Okay, and what happens is the conveyor belt goes this direction, a number goes in, and then out pops some other number, right? Well, composition of functions is kind of like lining up two machines, okay? And the first machine that is going to happen is G, right? That's the first machine that it goes through, and then it goes through F, okay? So we have a number X, and then out of G pops G of X, and then out of F pops F of G of X, right? And you can think of this as if I were to be in the factory, right, and I have this kind of a setup on my conveyor belts, if I put a huge box over all of this, okay, then for me, looking from the outside, okay, it would look like, well, one number goes in and one number goes out. So I'm just going to label this new box as a new function. Maybe you could call it H if you wanted. Or you could call it F of G, or F composed with G, something like that. Okay, so from two functions, we get a new function, okay, by just lining them up one after the other. Does that make sense? Okay, I think this tends to resonate a little bit better with people who have done some programming before and are familiar with the idea of a black box, right? It's basically like a black box. If you don't know what a black box is, don't worry about it. All right. So, let's move on. Okay, another example. Okay, GOF. Is that going to mess me up? No, that's not going to mess us up. We're too smart. So what's going to change for G of F? Yeah, I'm going to cube it first, right? The only thing that's going to change is I'm going to put a G where the F was, and I'm going to put an F where the G was, right? And to do that, I need to do G of whatever this is, right? So what happens if I plug 1 in to the F function? I get 1 cubed, right? Which is just G of 1, which is, as we found out in the last problem, that's 1 plus 1, which is 2. Okay? So what does this tell us? When I did F of G, I got 8. And when I did G of F, I got 2. So what's the conclusion? Order matters, right? Order definitely matters. We can't just do the functions in any order that we want. Okay. You can also combine or compose a function with itself, right? So it's kind of like if I put the number in and then I put the number in again, right? Whatever comes out. Okay, so I just take whatever goes through the f function, okay, and then I send it back through one more time, and then I get the answer, right? That's what I do. So that looks like the following. f of 1 is equal to f of 1 cubed, right? And 1 cubed is just 1, so this is f of 1, which is just 1. All right, so that was a whole lot of nothing. But you get the idea. If I did f of 2, then I would get f of 2 cubed, which would be f of 8. And then I would get 8 cubed as my final answer, which is like 512 or something like that. Okay. So now let's see how to find the formula in general, right? So before we said we can view the composition as an entirely new function, right? So if I look at it as an entirely new function, I should be able to find a formula for that function, right? So this is going to be the process by which we do that, okay? When I write f of g of x, I'm looking for the specific formula. So all I'm going to do is first rewrite f of g of x, because I don't like that stupid little circle. And now what are we going to do? Now I'm going to replace g by its function rule. Okay, I'm going to replace g by its function rule. So that would look something like this. F of x plus 1. Okay, f of x plus 1. Yes? And now all I'm going to do is, and this is a little bit confusing the first time you see it, but if you just remember what we're going to do, anytime we do f of something, we just take whatever that something is, and we plug with parentheses. Okay, that's all we do, is we take that something and we plug with parentheses. So the x plus 1 is going to get plugged with parentheses in for x right here in x cubed. Okay, so that would look like this. I put the parentheses around the x plus 1, and then I cube that. Okay? So this is a whole new function, right? This is a whole new function, which I acquired by plugging one function into another function. But I don't have to view it as a composition. I can view it as its own separate entity, which I can plug things into, right? So that's kind of like the yellow box perspective, okay? I put a hood over all of this stuff, and then I just ask, what does this thing do? Okay, that's kind of confusing, but hopefully that makes a little bit of sense. Okay, so let's try it again. Best medicine is practice for math. So this time we're going to do the other way around, right? We're going to take f of x, and we're going to plug it in for x in g. So I know what f of x is. It is x cubed, yes? And now, anywhere I see an... Okay, why can I not move the screen? There we go. Anywhere I see an x in g, I'm going to instead write x cubed, okay? With parentheses. So I get x cubed plus 1, which is just x cubed plus 1, right? Okay, so as you can see, the order very clearly matters, right? Because x cubed plus 1 and x plus 1 cubed are definitely not the same, right? They're definitely not the same. If I wanted to do x plus 1 cubed, I would need to FOIL twice. Yeah? I'd need to FOIL twice. I can't just distribute that cube onto both of these, can I? I would need to FOIL. Okay, so like we said, we can also plug a function into itself. So g of g would be g of x. And I know that g of x is x plus 1, so this is the same as doing g of x plus 1. And now what am I going to do? I'm going to take x plus 1, and I'm going to plug it in for... Whoa, not there. I'm going to plug it in for x right here, using parentheses. Right? So what does that look like? It just looks like x plus 1. Okay, that's my x, and then plus 1. So if I simplified that, I would get x plus 2. Okay? All right, so this is compositions of functions. This is how we evaluate compositions of functions at a point. Okay, so plugging in a number. And this is also how we get, okay, everything beneath this red line is how we get the function rule for the composition. So that was pretty thorough, I think. Are there any questions on that so far? All right, doesn't seem like there are. So let's talk about something more complicated. And this was probably the most complicated thing that we're going to talk about in chapter 1. And in my experience, students really don't like talking about the domain of a composition of functions because there's kind of a lot to unpack. But let's read the statement first, and then I have a picture, which is really kind of complicated, but okay, let's read the statement first. It says, the domain of a composition of functions, f of g, okay, so we're just composing two functions, is going to be the subset of the domain of g, which maps to an element in the domain of f. Okay, so what do we need to be true? If we're going to evaluate f of g of x, first and foremost, we need to be able to do g of x, right? If x is not in the domain of g, we're screwed from the start. But more so than that, we also need whatever g does to x, we get a new number, yes? And that number must also be in the domain of f, so that I can do the f part of the function. Okay, so let's see what the picture looks like. There's basically three important scenarios. Okay. All right. So nobody panic. This is more rainbow slide. But I tried to color code this, basically. Okay, so remember, what happens first? G happens first, right? And then F. Okay, so there's three scenarios. The first scenario is we have a number which, okay, I can plug that number into G. That's fine. And it just so happens that the output can also be plugged in to F, right? If this is the case, then the domain, or this point will be in the domain of the composition. Okay, so what we're looking for is I need to be able to go from the start to the middle to the end. Okay, so what's a situation which is not so good? Well, there could be something like 2, right? Which, okay, you're allowed to plug 2 into G, but there's no way to get from the output of G to the output of F, okay, because 5 is not in the domain of F. Okay, so it's possible that you do f of g of x, and everything goes nicely when you do g of x, and you get a new number. But that number is not allowed to be plugged into the function f. So that's option 2. Okay, option 3 is it's possible that there is a number which is in the domain of f, okay, but there's no number in the domain of G such that if you plug it into G, you get that number, okay? So that's another situation you can run into. And then, is that the last one? I think so. And then finally, there's one more option, which is that there's a number 4 or something like that, which is not in the domain of G. And then it's just, you're really screwed, right? There's no way you can even plug it into G, let alone get an output that you could also plug into F, okay? All right, so the domain of the composition is, of course, going to be those numbers which are in the domain of G, which have an additional property, they must map to a member of the domain of F. Okay? They must map to a member of the domain of F. All right, maybe we should practice with an example. Yeah? Okay, let's do an example really quick. Oh, there we have one right there. Never mind. Okay, we'll do that example after I talk over the range. Well, the range is really simple compared to the domain because all the hard work is in finding the domain. Once you have the domain, all you have to do is consider what is the set of all possible outputs if I plug in a given input from the domain. Okay, so once you have the domain, you just check, okay, what is the set of all the outputs that I could get by plugging in a number from this domain? Okay, any questions on the definition before we see an example? Okay, I still see some people writing, so I'll keep this on the screen for a second. Okay, so yeah, I mean, the range of any function is just, you just need to find the domain first, and then plug in everything in the domain. Of course, you can't go about plugging in literally every number in the domain. It's impossible if your domain has infinitely many numbers in it, right? But you can have an idea of which numbers in the domain are going to produce the smallest outputs versus the largest outputs. Are there going to be any gaps and these sorts of things? Okay, are we ready to move on to the example? Okay, cool. So let's find the domain and range of f of g of x. Okay, well, we know that we're going to need to do f of g of x, right? So I think the first thing that it would be useful to do, okay, would be to ask ourselves, what is the domain of g? Yes? Ask ourselves, what is the domain of G? So let's try to describe that first. Okay, domain of G is going to be what? What are all the numbers that I can plug into G? How can I express that? Say using interval notation. All real numbers except 5. So in interval notation, what would that look like? I need to use a union, right? Okay, good. And another way you could write this set would be to say R and then set minus 5. Okay, so this is like all the real numbers except 5. Okay. All right, so that's the domain of G. So now we need to consider why don't we talk about the domain of F first? Okay, let's talk about the domain of F. All right, what do we think for the domain of f of x? Yeah, 0, comma, infinity. Should I have a bracket on 0 or should I have a parentheses? When should I have a bracket versus when should I have a parentheses?
Bracket is when you're including it in the set.
Very good. Bracket is when I include it, right? If I'm going to include 0 into this set, what must be true? I must be able to compute the square root of 0. Can I do the square root of 0? You can do the square root of 0. It's just 0. Because the square root of a number is any number such that if I multiply it with itself, I get 0, right? So 0 clearly fits that description, right? Because 0 times 0 equals 0. Therefore, take the square root of both sides. You have 0 squared equals 0. Take the square root on both sides, and I get 0 equals the square root of 0. Yes? So it's okay to do the square root of 0, so I'm going to put a bracket here. All right. So now, we know what is the domain of G. We know that the domain of f of g of x is going to be a subset, okay? A subset of this domain, okay? So how do we figure out what it is? We need to consider the other condition. It's the subset of the domain of G such that when I plug the x value in to G, I get a number which can be plugged into F. So what kind of numbers can be plugged into F? It's all the positive numbers. So I need to consider what are the numbers which, if I plug them into G, result in a positive output. Yeah? So what's the subset of these numbers such that if I plug them into G, I get something positive? Yeah, x just needs to be a number which is bigger than 5, right? Because if x is a number smaller than 5, what's going to happen? The denominator will be negative, yeah? And if the denominator is negative, then the whole fraction is negative because the numerator is positive. So I need to consider, okay, I only want the values that are in this set and are larger than 5. So that's exactly all of these ones, right? And none of these ones. Agree? So g of x is in the domain of f only when x is bigger than or equal to 5. Okay? Only when x is bigger than or equal to 5. Therefore, domain of f composed with g is going to be 5, infinity. Okay? 5, infinity. All right, so let's take a look at how that works. So what would happen if I computed f of g of x using the function rule? Well, it would look like this. It would look like f of 1 over x minus 5, yes? And then f is to do the square root, right? So this would look like the square root of 1 over x minus 5. Okay? So that would be the function rule. So you can see exactly why we need the domain to be this. Because first of all, we need to not divide by 0. So x should definitely not be 5. So we exclude 5. And then what needs to be true? Whatever's under the square root needs to be positive, yes? Or at least non-negative. So it can be 0. But 1 over x minus 5 will never be 0. But that's besides the point. So we need this number to be positive in order to be able to do the square root of it. Okay? So basically you get two things. You get x minus 5 should not be 0, and you get x minus 5 should also be larger than or equal to, not larger than or equal to, it should be larger than 0. Yeah? Or 1 over x minus 5 should be larger than 0. They're both the same. Okay, so that is how we get the domain. So now we've found the domain. Let's talk about the range. Am I running out of time? No, I got time. I'm hearing so much zipping. Okay. The range. How are we going to do the range? Well, we are going to take the domain, which we already computed. It's 5 to infinity. So, and we're going to ask ourselves, what kind of numbers can we get as an output by plugging one of the numbers from 5 to infinity in to the function square root of 1 over x minus 5? This is the question that we need to answer in order to find the range of the composition. Okay? All right, so what is... Okay. I think a useful thing for finding the range is to think about... Yes?
I actually believe I emailed you why. And everything.
Okay, yeah, that's fine. Yeah, go ahead. Okay, so we want to think about what is like the smallest outputs that we can achieve and what are the largest outputs that we can achieve, and are there any gaps? Okay, that's basically what we want to think about. Okay, so when I look at this, I think, okay, I'm taking the square root of a number, right? So the smallest possible output is going to be attained whenever whatever's under the square root is smallest, right? How can I make 1 over x minus 5 really, really small? If I want this fraction to be extremely small, then I want x to be what kind of number? Not well, okay. It can't be negative, right? Because I need to make sure that the number I plug in for x is somewhere between 5 and infinity. What happens if I plug in something close to 5? Then the denominator will be close to 0. And then, therefore, this number will be very big or small? Very big. If the denominator is extremely small, then the fraction is extremely big. Yes? It's like if I do, for example, 1 divided by 1 over 1 million, right? What would that be equal to? That would be equal to 1 million. Yeah? Okay, so when x is very close to 5, this number becomes very close to 0, not 0, infinity, right? It gets bigger and bigger and bigger the closer we get to 5. And how about if we make x really, really huge, like a billion? Then the denominator will be what? Really, really big or really, really small? Well, if x is extremely big and I take away 5, it's still big, right? So if the denominator is huge and the numerator is small, what kind of number do I get? An extremely small number. Can I ever get 0? Well, if I plug in 5, I would get 0 in the denominator, which is not allowed, right? But I mean, can I ever make the fraction 0? No, you can't, right? You can't make the fraction 0. You can divide by as big of a number as you want, right? But you can never find a number so big that 1 divided by it is 0. It's just going to be a fraction which is just barely bigger than 0, right? Okay, so I think 1 over x minus 5, okay, is going to be a new number which is larger than 0, right? Because we can never make this number 0. We can never make this number 0 no matter what we plug in for x. So the number is always going to be larger than 0 since I'm plugging in a number which is positive or greater than 5. And also can be as large as we like. Okay, so you can loosely think of the range of this function as being like the range of this function goes from 0 to infinity, basically, right? So if I take the square root of a number which is between 0 and infinity, what kind of number will I get? I will again get a number which is between 0 and infinity, right? Because if I want to get the number to be extremely big, right, no matter what number I choose, like if I want 1 billion, then I just need 1 over x minus 5 to be 1 billion squared. If I want the square root of the thing to be 1 trillion, I just need to find the number x that makes 1 over x minus 5 1 trillion squared. Yes? So I can make the square root as large as I want as well. Okay, square root of such a number will be in the set 0, infinity. Okay, dare I ask how we feel about that? It's kind of a lot, I agree. But I think where we want to start is always with the domain, okay? And I think the domain, even though it's really complicated, there's a good process for doing it, right? I just need to find the domain of G first, the inside function, and then I take the subset of that, which maps to a viable input for f. Once you have the domain, you just need to consider, okay, what kind of outputs can be produced by an input in the domain? And that's how we get the range. Okay, any questions on domain or range of compositions of functions? Are we confused by this? Let's have some thumbs. I want to see the thumbs. Thumbs down if you hate this, and thumbs up if you're kind of okay with it. And thumbs in the middle if you're in the middle.
What if you hate it, but like you could do it?
Yeah, let's have thumbs up for I feel like I could do that on a quiz tomorrow. And thumbs down for I would definitely fail that quiz. Okay, yeah, that's about what I expected. I think it's a tough topic. But, you know, with any of these tough topics, which this is probably one of the hardest ones that we do in the whole semester, is finding the domain and range of a composition of functions. But it's important, and it will continue to be important if you go and take calculus. So don't feel like you have to have an amazing understanding of this, but when you do the homework, hopefully you'll get some practice in and you'll feel a lot better. Okay. Is it okay for me to move on? Or maybe we should do another example? No? Okay, let's have a vote. Who wants to do one more example of that? And who wants to move on? Okay, that's a resounding move on. If you want to talk more about this, we can talk about it in office hours today. Okay, let's talk about inverse functions. Okay, so inverse functions are really just about undoing, okay? Any process that we can do, a lot of the time we can undo, right? Especially if I'm in like in a factory setting where I have my machines, right? I might want to have one machine that does something, and then I might, just in case I accidentally put something into that machine and I want to undo whatever I just did, I need to have another machine which could reverse that process. Okay, so we're going to talk about how do we reverse the process of plugging a number into a function. And the answer is we use another function. Okay, and that function is called the inverse. Okay, that function is called the inverse. Okay, but there's a massive, massive hang-up with inverse functions. And the problem with inverse functions is that sometimes they don't exist. And you can't actually undo whatever that process is. Okay, you can't actually undo whatever that process is. So this really comes down to a property that a function can have. And if we have that property, then we will be able to find the inverse. And this property is called one-to-oneness. Okay, so we do one-to-one with dashes like this. And what one-to-one means is, roughly speaking, exactly one input will map to exactly one output, right? So in math speak, what that means is if two inputs are different, then their outputs are also different. Okay? So here's an example of two functions, one of which is one-to-one and one of which is not. Here's the one-to-one, okay? It's one-to-one because for each input, okay, not only is there exactly one output, it's also true in reverse. For each output, there is exactly one input, okay? Here's an example of when that is not satisfied. This is a function. It passes the vertical line test. That's totally fine. For each input, there is exactly one output. But for each output, can you find another input which is going to find this as the output? Yes. It's going to be this input, right? Here's x1, which is not equal to here, which is x2. But their outputs are equal. Okay? So why is that a problem when we do inverses? Well, if I plug a number into a machine and I get a new number out, and my boss asks me, I see this number that you got out of the machine. What number did you plug in to get it? Well, it could have been either of these two numbers, really. And it's hard for me to answer that question without some foreknowledge, right, of what went into the machine. If I just look at the output and I ask, well, what was the input that produced that output? I can't answer that question because there are multiple possibilities. Okay, so this is why one-to-oneness is important for finding inverses. So how can you tell if a function is one-to-one? It's the easiest thing in the world. If you have a graph, you just check if it passes the horizontal line test. Okay, so vertical line test tells us, what does the vertical line test tell us, actually? Yeah, it tells us whether a relation is a function, okay? The horizontal line test will be used to tell us whether a function is one-to-one. So what do? I just take my pencil, which here I've drawn an abstract pencil, okay? It's just a yellow line. I take my pencil and I put it down on the paper and I check. Aha, it only touches at one spot, one spot, one spot, one spot, one spot, one spot. Okay, it's one-to-one. On the other one, what do? I go, okay, one spot, one spot, one spot, one spot. Oops, now I'm touching the graph at 3 different locations. So the horizontal line test has failed. Oh no, our function is not one-to-one. All right, so that's when we use the horizontal line test. It's for checking. Why don't I leave it up here for the purposes of looking back at the notes? I use the horizontal line test to check if the function is one-to-one. Okay, great. So this is all about reversing the process of a function. If I'm going to reverse it, I need to make sure that there's only one possible input that produced that output. So let's see some more facts about inverses. Okay, so this is just a bunch of nonsense, not nonsense, but it's a bunch of words that you don't need to write down. If f of x is one-to-one, then the inverse function, okay, the inverse function f -1 of x, okay, so this is how we write it. Okay, we write a little -1 up here. Okay, which, by the way, this does not mean 1 divided by f of x. Okay, I know that's extremely confusing because someone somewhere in the world, like hundreds of years ago, did not have very much foresight into understanding why this is so confusing. I'm not sure why. But I just want to point out that this is not what this means. If I write a -1 up here, I'm talking about the inverse function. Okay, so what is the inverse function? It is the function defined such that if the output of f of x is y, okay, then if we plug y in to the inverse function, we get back x. Right? If I plug in y, I get back x. All right. So let's talk about the domain and range. Well, of course, what are the inputs going to be for the inverse function? The inputs of the inverse function are all of the outputs of the regular function. So the domain of the inverse function is just going to be the range of the original function. And vice versa, right? The range of f inverse is going to be the domain of the original function. Okay, so that is the domain and range of an inverse function. So, loosely speaking, if we have a function f of x and f of 2 equals 3, then I immediately know what f inverse of 3 is going to be. What is it going to be? 2, right? Okay, so that's how the inverse function works. By the way, the inverse of the inverse function is going to be what? The original function, exactly. So the relationship goes both ways. They are inverses of one another. Okay, it's just a matter of perspective in terms of which one you view as the original function. Okay? All right, so let's try this practice. Okay, so I want to know, how do I figure out what the inverse function... Oh, well, actually, maybe we'll talk about this next time because I'm kind of out of time. All right, we'll stop there for today. I have office hours later.